Okay, so this is an introductory lecture on the many-body problem. And when you have many bodies, of course, you can use more than one approach, right? But since this is the Yambo school, and you will hear a lot about Green's functions, the Green's function formalism is one of the many-body methods that one can use to solve or to try to solve the many-body problem. Now, so this is an introductory lecture on Green's functions. I decided to use a little bit of an unorthodox way of introducing the Green's function. I'd like to start, let's say, from something we really need to calculate, okay? So, I mean, we do an experiment and for absorption, and we know that the absorption line has something to do with transition dipoles, that dipole averages that are oscillating in time, or we do a for emission experiment and we know that we need to calculate the density of electrons with a certain value of momentum k going out from the sample. So we need to calculate something, an observable quantity that is useful to make contact with experiments. Just take an example, okay? So I use here the density because I guess everybody knows here how to calculate or what it looks like, the density operator. And this is one of the objects that is useful to make contacts with the experiment. Now you might wonder why I didn't call the density n. And that's something you should ask to the converter from Keynote to PowerPoint. So this symbol over there, just on the left of psi dagger psi, is n. It's new to me too, so let's get used to it. That's n from now on. Okay. Now, yeah, we expand. N is the product of psi dagger psi. You know that you can expand each of these field operators in some complete basis, and therefore, what we are interested in is in calculating the time-dependent average of this operator. The time-dependent average means that we have to evolve the state, a state from which we start, could be phi, this capital phi. We evolve it from some time t0 to some other time t, and the reason why this evolution might be not trivial is because you are shining a laser on your system, and then you average the density operator. So this is your goal, is to calculate this object. And okay, just for brevity, we call it phi of t, the evolved state. And then we insert the expansion inside this average. And you see that then the goal becomes to calculate the average over phi of t is of this operator, d dagger k dk prime. Which and this is actually for pedagogical reason, I found it much more useful to convert it into the average of d dagger for you. But you know, I mean, you can use the anti-commutation rules between these two operators, and you can write this object also as the average of d and d dagger. Okay, so this is your goal. And now is the trick. Now this is the fundamental point in many-body theory. It's really the starting point. What you do now to calculate this object is to insert between d and d dagger an evolution operator that goes from time t to minus infinity, and then from minus infinity back to t. This idea is actually very old, but this, say, going back and forth is something that led to a fundamental concept called the contour, and was initially, well, let's say, I wouldn't say is initially introduced by Keldysh, but today is known as the Keldysh contour. This is something you don't need to know. That's written here on the slide is really the only thing you need to understand. You just insert an identity between d and d dagger, but as many of the progresses in science and in physics, in theoretical physics, consist in writing either 1 in an intelligent way or in adding 0 in an intelligent way. And this means we have just added 1 in an intelligent way. You from t to minus infinity times u from minus infinity to t. So this is our final goal. We just don't like this minus infinity appearing all over. Just call it u of t. And that's the object we want to calculate in order to make contact with some experiment. So we have to say something about this evolution operator. I mean, it's pretty obvious that we need to be able to understand something about the evolution operator. Now here we consider the evolution operator, of course, satisfies the Schrödinger equation. And of course, we can solve the Schrödinger equation only for trivial cases. In the majority of the cases, the Hamiltonian is the sum of two pieces, one which we call T, that you assume to know, and another one which we call V, that we want to treat perturbatively, many-body perturbation theory. Okay, so U0 is the evolution operator of a system described by this Hamiltonian that we call T because I'm thinking about the kinetic energy, and we know it. We write U, the full U, as the product of U0 times something we don't know, so we put all our ignorance in F, and we generate an equation of motion for F, where it appears this V written in the so-called interaction picture, and we integrate this equation and find an expression that is perturbative for the evolution F. Okay, so this, in principle, if you continue the series all the way to infinity, this is the exact form of F, but this is a nice formula because it allows us to treat what we don't know, V, in a perturbative manner. Notice that in this formula, the times are constrained. So we have a time t1 that is smaller than t, and then a time t2 that is smaller than t1. That's very annoying. Okay, now consider the simplest possible example. I mean, as I said, t and v can be anything. Okay, you can use this for this way of approximating the evolution operator for any kind of problem. You can have many particles, but also just one particle. So let's assume we have just one particle, and we write the Hamiltonian as t plus v, and t is the kinetic term, v is some scattering potential. And again, in the purple box is the object we are interested in calculating. Okay, let's focus on one of them, u dagger d dagger phi. Now, we rewrite this with the formula we have derived for the evolution operator. Of course, we have to take the dagger. And then we expand F. And that's what we find. And at this point, all these beautiful pictures that are called Feynman diagrams come in. Because the idea now is to represent every term in these mathematical expansions with a drawing, okay? Which is much easier. And then we simply provide rules to convert a drawing into a mathematical expression. That's all what it is, Feynman diagrams. So what we do now is to represent what we can say is the free propagation, because there is no v here in this term. This simply provide a simple propagation of a particle, d dagger k, acting on phi. It means that we have added a particle of momentum k over the state phi, and we just let it propagate freely, without any scattering potential. And we represent this term with a line, an oriented line going from time t to minus infinity, and we put this label k to say that we have created a particle of momentum k. That's what it is, okay? Okay, but if we decide to have this expression to represent the propagation, then this other term this second drawing is what it represents, the second term, because we have again a propagation from t to t1, you see. T1 is exactly the time at which the operator v, the scattering potential, is calculated. This v is represented with a circle crossed, and then at time t1, electrons with momentum k can scatter in any other momentum. And therefore, we have to sum over all possibilities. That means we have to sum over all k1s, and then the evolution continues freely to propagate until minus infinity. And in this way, we can also represent the second term. Again, notice, these are all intermediate states. called intermediate states. And again, notice that the times are here constrained. And so we have just invented a graphical picture to represent this mathematical expression. Okay, now we can go back to our goal. We have to calculate the overlap between this cat, which we have represented diagrammatically already. So here you see the very same thing I showed you in the previous slide. I just omit to write sum over k, integral in dt1. These are all rules that comes when you convert a drawing into a diagram, okay? When I mean, you have to be short, right? So every drawing implies that you integrate over times, every internal cross, that you sum over all case, every internal lines. These are just detail. Forget about them for the time being. Look at the drawing. So this is the cat, if you want, and then you have to take the scalar product with a bra, but the bra is exactly the same thing. You simply have to change k with k prime. So this is what you have. You have to take the scalar product between these two quantities. And that's something you can do. You sit down with a piece of paper, and you find out that you can actually derive very nice gluing rules that allows you to merge, for instance, the zeroth order form in this form. I will come back to those gluing rules, okay? But they are simple, algebraic, nothing to be scared. And this would be the zeroth order term. And then you have to find the first order term, that is simply the product of the first and the second and the first. And when you use the gluing rule, the beautiful thing is that now the integral over T1 is no longer constrained. You integrate it from minus to plus infinity. It's no longer constrained. And then, of course, you can go on and find out all the terms of second order and all the terms of third order and so on and so forth. And you find this expression here. Again, the important thing is that with these gluing rules, I'll come back to them. It's just a technical point. You have this expression that stems naturally from the overlap or from the scalar product between a cat and a bra. Okay, now what was special in the previous slide about taking the cat at time t and the bra at time t? Absolutely nothing. We could have taken the cat at time t prime and the bra at time t, and we would have got exactly the same expression. But if we choose the time at different the times differently, this object now all of a sudden get a name. We give it a name to this object. We call it the greater Green's function. It's not like Alexander the Great, so it's not more important than the lesser. It just means that typically this object is used when the time t is larger than t prime. That's all, okay? But it's not always like that. Okay, and so as I said, we have already calculated this object. We now represent it too. Is represented with this double line, and I rewrite exactly what was written in the previous slide. So it's this nice series, but you recognize that this series is actually an iterative series, and therefore can be resummed in this nice way, and you find out a kind of Dyson equation. G is G0 plus G0 VG. I mean, an equation that you must have seen, I don't know how many times. It just, as I said before, come out from taking the overlap between a cat and a bra. Okay? So we really, inside this equation, we really have to think there is the square of what we think is the propagation of a single particle state, the cat or the bra. Okay, now, what really means G0 VG? We have to know the gluing rules. And this is the only slide where there is a little bit of technicalities. In addition to this greater Green's function, okay, where we have the d dagger operator on the left and the d operator on the right, we can construct in exactly the same way the lesser Green's function, where the d operator is on the left and d dagger is on the right. Exactly the same thing. We simply exchange d and d dagger, no more than that. One is called the greater, the other is called the lesser. These are the most fundamental objects because these are the only quantities that can be measured, not a combination of them. Unless you are at zero temperature, but this is a technical point. Now, once you know the greater and the lesser, you can subtract them. So it's nothing, you don't introduce new objects, okay? You simply subtract them, okay? If you know greater and lesser, you know also the difference between them. And what you define the retarded Green's function is this difference times the theta function, the Heaviside function for t larger than t prime. So in a way, you have to imagine the double time plane, t and t prime. The retarded function lives on half of this plane. The advanced function lives on this other half of the plane. But if you put them together, they reform the difference g greater minus g lesser. No more than that. Okay, now we are ready to say what this Dyson equation really means. It means this. So we don't simply have to multiply g0 times v times g, but we have to, for instance, for the greater Green's function, take g0 component retarded times v component greater, and then g0 greater times v component advanced. As you see, instead of g dg, you have, so one term, you have two terms. And they appear with this nice suffix or superscripts, okay, that come out from the algebra when you do the gluing rules. I cannot derive them, okay, right now because it takes maybe a couple of hours, but just take them, okay, just accept them. If you are interested, I can tell you where to read about them. Of course, as I said before, once you know the greater and the lesser, you know also retarded and advanced. So if you take these two equations here and you take the difference, you find this equation that is much simpler now for the retarded component. As one say typically is that the retarded Dyson equation or the advanced Dyson equation is much easier because it contains only retarded objects. Instead, the greater and the lesser Dyson equation contains a mixture of the objects. And what about the most familiar Green's function, where everyone, lots of books, 90% of the books tells us about the time order Green's function, the most famous ones. Well, the time order Green's function is obtained by taking this funny combination, greater plus advanced, you really get it, or a lesser plus retarded. And if you use these rules, what you actually find is not just time ordered v time ordered, but you find an extra term, this term. And why you have never seen these terms? You have never seen this term because this term actually vanishes if you work in equilibrium and at zero temperature. So the moment you want to work out of equilibrium and at finite temperature, you have no way, I'm sorry guys, you have to learn the gluing rules. Let's come to interacting system. This is a lecture on the many-body problem. And I'm sure you're really disappointed so far because you have seen just one particle. So interacting systems, many particles. This formula for the evolution operator is exactly the same, right? We didn't say what is T, what is V. Now we say what is T. T is the sum of the kinetic energy, V is the interaction energy. Okay, let's apply the same idea of representing each term of this expansion with a graphical object. So the first term is identical to the one we had before. It's the free evolution of an added particle of momentum k over the ground over some state phi of t. Okay, we are adding the d daga k over phi of t, and we are propagating it. Now, what is the difference about the second object? That now we are not scattering the electron against a scattering potential. We are scattering the electron against another electron. So if we want to represent this second term, there is no way. We have to account for the scattering with the second electron that is already in the system. So that's the proper way of representing this diagram. Look, it's completely different, the nature of the interaction. Before we have an interaction depending only on one R. This interaction depends on Ri and Rj. It's denoting the scattering between two particles belonging to the system, not against an external potential. And after the scattering, that is this wiggly line that represents the Coulomb interaction, these particles scatter into two other states. Okay, so this is the proper way of representing this term. So Another way of seeing it, that maybe is more familiar to you, is that if you add a particle of momentum k in the system, this particle can scatter an electron, the original electron change momentum, but you also create a particle hole. And the particle hole is this object here. And all of a sudden, from one particle, you get two particles and one hole. And then, of course, you have to sum over all the intermediate states, and you start getting to see between the fade and the fog the origin of the Feynman diagram using this a bit unorthodox derivation I'm presenting here. And of course, then you have second order contribution. And now, a difference from before, you have different way of scattering. This is a typical diagram, but you can also have this other type of diagrams. Okay, you have to consider all possible ways when you scatter an electron, and each electron goes into another electron plus a particle hole, and it can do it in different ways. And again, look at the times. These are all time that contains constrained integrals. Okay, let's focus on the first order pieces. The second order is already too boring to work out in an introductory lecture. So this is what we have to calculate, always the same thing, the scalar product between the ket and the bra. And again, we can use exactly the same gluing rules we have derived in the case of just one particle, because the gluing rules are algebra, do not know anything about how many particles do you have. So you start enjoying like a baby or like a kid that starts drawing on a piece of paper and just glue in all possible ways. So you can glue this and you get the so-called non-interacting Green's function, so the free propagation. You see, that contains no interaction, exactly like we were gluing before. Or you can glue in this way, and you get this diagram. Or you can glue in this way, and you get this other diagram. The second is called the Hartree diagram. The second is called the Fock diagram. Or you can glue in this way, and you get the so-called first bubble diagram. Or you can glue in this way, and you get twice the tadpole or Hartree diagrams. Or you can glue in this way again, and you get what is called the second order exchange diagram. And you see, it's really like a game, right? You can just glue back and forth all possible lines, just consider all possible way of gluing. But the nice thing is that the bra contains all possible scattering events, the ket contains all possible scattering events, and then you have to just glue the scattering events in all possible ways. And this, as you see soon, is the real content of an object that otherwise lose completely the any physical significance, and that is the so-called self-energy. What is the self-energy? You see that in this diagram, there are some diagrams that is more special than other because it's so-called one particle irreducible. You cannot cut them by cutting an internal line. So we call these diagrams 1PI, one particle irreducible diagram, and these are exactly what people call the self-energy. This is an example of one particle reducible diagram because this can be cut in two by cutting this line. And therefore, this object can actually be written as the product of a self-energy times a G times another self-energy. And of course, when you really do the expansion to all order, you have all possible irreducible pieces connected by a line, connected by other irreducible pieces, and so on and so forth. So at the end, when you really work out the scalar product and you represent it with a double line, you get this type of series. And again, exactly like in the one particle case with the scattering potential, you recognize that this series is an iterative series, and you can easily form from the scalar product between a ket and a bra the so-called Dyson equation. Okay, so I hope in this way should be clear, or better clear, what type of information the self-energy contains. Is in essence the probability amplitude that a scattering event is contained in another scattering event. And so if you already know what kind of scattering are relevant in your dynamics, you can actually enjoy drawing first the important scattering and then taking the specular object and then gluing in all possible ways. And this self-energy will contain the scattering events that for you and for the problem at hand are important to include. An example is GW. What kind of scattering event is contemplating the GW approximation? Well, it contains essentially this type of scattering event. A particle interact, create a particle hole. And then you see what happened. The particle hole reinteract and create another particle hole and leave this particle here, there on the bottom completely unchanged. And that's the reason why it's so easy to go from GW to a static version of GW that somehow mimic the same mathematics of the Fock approximation. And of course, I still didn't show you that this actually is the GW approximation. You have to take a scalar product between the ket and the bra, and now you see that by gluing only the bubbles, the lines that contains the bubble, you end up with a lot of bubbles, only bubbles. You sum all the bubbles, and the sum of all the bubbles is called W. Another example is the T matrix. This is relevant for other type of problems. This is relevant, for instance, in when you want to study, for instance, excited semiconductors hosting excitons. This is an example of application. Or another example, if you actually revert it, because this is in the so-called particle hole, this is actually in the particle-particle channel. So this is relevant not for that problem. This is relevant when you study superconductivity. If you want to explain microscopically the formation of a Cooper pair, that's the type of diagram you have to consider. So you do the scalar product between these two types of diagrams, and you get the so-called T matrix approximation. Okay, gluing rules. What is the difference between the gluing rules here with the one I have already told you? There is absolutely no difference, except for one thing. V is a one-time object. The self-energy is a two-time object. So how do we face with this problem? That's actually very simple. V is a one-time object. This means that the product of G times V, G0 times V, is a two-time quantity. Keep that in mind. And here I rewrite simply the equations I have already shown you before. So if you want to write the Dyson equation for the greater Green's function, that's what it means. And for the retarded Green's function, that's what it means. Now, these gluing rules, for some reason, are applied by a lot of people. They are derived also by a lot of people. But I mean, the first time a student wants to learn about these gluing rules, it's very hard, have very hard access to the derivation, because all these people using these gluing rules keep the derivation jealously in their drawers. So we didn't think, I mean, we believe in free flow of information, so you can find in our book a very pedagogical introduction to these gluing rules. That's why I put this, very disappointed by this attitude of not showing the derivations. So what does it mean, the Dyson equation here? Again, G0 sigma is a convolution, so also G0 sigma is a two-time quantity, like GV0. So therefore, we can really follow the same rule. Compare with the top equation in this slide. You have G0 greater, then you treat the product, the convolution G0 sigma, you treat it as the same, the object in the circle, okay? It's a two-time object, so it's the retarded plus this object, again, convolution is greater. And now you have to break what is in the square brackets, because G0 and sigma are separately two-time objects. So how do you break them? You use the fact that two retarded objects convoluted are just a retarded object, and you use the first equation to break what is in the square bracket, and you get this expression here. So this would be the Dyson equation for the greater Green's function, and a similar one for the lesser Green's function. Nothing would change for the retarded Green's function, always written in terms of retarded quantities only. Now, completely agree with you. It's too complicated for implementation, this equation. Absolutely, no doubt, okay? But that's what it should be when you are out of equilibrium and at finite temperature. Does it mean that we shouldn't use it, or there is no other way to do it? Of course, You wouldn't have been invited in this school if this was the case. So the idea is to convert this equation into a differential equation that is more suitable for numerical implementation. And this idea leads to the so-called Kadanoff-Baym equations. Now let me restart from here, and let me, for simplicity, assume that there is lattice that we deal with lattice periodic system, so that this object, the Green's function, is diagonal in K-space. And now we use the equation of motion for the greater and the retarded Green's function in non-interacting system. These are non-interacting system. Everything is simple when it's non-interacting. These are actually two equations that you can derive extremely easily. I mean, if you are interested, 15 minutes we can derive this equation. Okay, it's non-interacting. Everything is simple when it's non-interacting. Now let's use these two equations to rewrite the equation that is on top of the slide. So we take I ddt minus epsilon k acting on the left-hand side, and I use this equation, of course, to cancel the first term, because when I apply that, I get 0, right? And I use the second equation to rewrite this object simply as the convolution between retarded sigma and g, because, yeah, you see here, is a delta function. So integral of a delta is like no integral. And again, this is 0 because I use this equation. And then again, just the second piece there. So this is the differential equation that the greater Green's function satisfies. In a similar way, you can derive the differential equation for the lesser Green's function, and these are called the Kadanoff-Baym equations, and they represent an exact reformulation of the many-body Schrödinger equation, with one big advantage. The Schrödinger equation is an equation for the wave function that for macroscopic system contains on 10 to the 23 variables. Here the Green's function contains only 2 spatial variables 2 times, okay, much less than 10 to the 23, plus, and I see this as an advantage, you have the possibility of systematically approximating what is the main cause of the problem, the self-energy. The self-energy contains the information you decide might be relevant for the scattering, for the dynamics or for the system you have at hand. It's your physical intuition can be nicely translated into a drawing, and then the drawing is nicely translated into a mathematical expression that you plug into the self-energy, and then you solve the equation. And that's, in essence, many-body perturbation theory. Now, we started with the fact that we needed something to make connection with the experiment. But it turns out that the Green's function for times t different from t prime has a nice physical interpretation, even if t is not equal to t prime. Let's have a look at it. So in the first line, you see, again, the very same definition we have already used many times. And since I'm lazy, I don't want to rewrite u of t primes times u dagger of t. I simply recognize this is the evolution operator from time t to time t prime. So let me just call it u of t prime and t, okay? And now I reinterpret this object in a slightly different way. So look at the bra, transform this bra into a cat. So this means when transform into a cat, you are not adding, but you are removing a particle of momentum k prime. What does this mean? Phi of t prime means that we are propagating the system from time t0 to time t prime, and at time t prime we are removing a particle of momentum k prime. So let me represent in k space this situation in this way. Okay, we evolve from t0 to t, the many-body state, and at time t prime we remove a particle of momentum k prime. Now let's have a look at the cat. The cat tells you something a little bit different. We evolve the state, phi, from time t0 to time t. At time t, we remove a particle of momentum k. And then, of course, this is an animation. Ah, it's working. And then we let the system propagate from time t to time t prime. and then we take the overlap with the state that is on top. So what has happened? That from time t to time t prime, if the system is interacting, this particle had time to scatter with many other particles. So in k-space, if you work in k-space, the probability of finding this particle exactly at k is actually spreading. It's spreading like a drop of ink in a glass of water. Okay, it's just spreading. So you see that when you now take the overlap between these two, when you expect this probability amplitude to go to 0 if the distance between t and t prime approaches infinity. That's exactly what happened in macroscopic interacting system. And this has a nice connection with the picture. This time picture has a nice connection with the frequency picture. Let's see why this is so, in what way this physics manifests itself in frequency space. Now, in frequency space, there are a few mathematical theorems that you can use to calculate the Green's function. One is called the fluctuation dissipation theorem that relates the lesser Green's function to the retarded Green's function that is written here. But that's not so important. And the retarded Green's function satisfies a Dyson equation we have already seen. So I just write it, the Dyson equation for the retarded Green's function is explicitly in frequency space. Now, the retarded Green's function can be always written like any complex number into a real and an imaginary part. So we plug it in there, and this is the final expression we get for the lesser Green's function. Okay, now, consider the system as non-interacting. What happened? That gamma goes to 0, lambda goes to 0, and so on. So we just get this simple expression, the Fermi function times a Lorentzian. Eta is a small object. We can take it as small as we want. And a Lorentzian with a very, very narrow width becomes a delta function. That's what we have. OK, now we insert the Fourier transform into the time picture. So G lesser of t and t prime. It's just the Fourier transform of G lesser of omega. There is nothing better than having the integral of a delta function because we don't need to do any integral. And what we get is just the Fermi function times an exponential. So that probability amplitude of the previous slide is certainly 0 if we are going to remove a particle that is already not there. So that's the meaning of the Fermi function. The level k must be occupied. But if it is occupied, the square of this object, which is the probability, this g is just the probability amplitude, the square of this object is independent of time. And what is the physical meaning? That if the system is non-interacting, we add a particle or remove a particle of momentum k, and we let the system propagate, nothing changes. The probability of getting the same state after a time t minus t prime is always the same, because this particle has no way to scatter against the other particle, because it doesn't interact with the other particles. Okay? So no decay in time means sharp peaks in frequency space. What happens when we are, and so typically one say in this case that electrons with momentum k has an infinitely long lifetime. What happens when we are interacting? Now in this case we cannot take gamma and lambda to be non-vanishing. Well, typically one defines the quasi-particle energy capital E as the solution of the real part of the denominator equals 0. But then you can expand the real part of the denominator in this way, plug it into the expression for G lesser, and find this expression here. This is a kind of renormalized Lorentzian. There are several interesting things in this expression. First, this Lorentzian is not normalized to unity, like it was the delta function before. This is called the quasi-particle weight. What is happening here is that if we add an electron in the system and remove it after some time, the probability, even if the time at which we remove it is super short, there is no way this electron is not a good particle. So we remove it, and somehow this electron is not just an electron, it's an electron plus something else. And somehow the electrons, when there are many, many, many particles, there is really not a real physical meaning we can attach to the elementary particle. Elementary particles put together are not so elementary anymore. They become so-called quasi-particles. And Zk tells me how much of the old elementary particles there is still in the system. And Tau k. Tau k is what before was infinitely long lifetime in the non-interacting case. This object instead tells us that when the difference between t minus t prime approaches infinity, this probability amplitude, like the drop of ink in a glass of water, is actually spreading and the overlap approaches 0. And that's very easy to see. You just plug it into the Fourier transform for the lesser Green's function, and you clearly see that in addition of a purely imaginary exponential, you also have this term that goes to 0 exponentially fast with a lifetime tau k. Zk before was 1, and now is in general an object between 0 and 1. And this should be compared with the expression we had before in the non-interacting case. You see there is no Zk here. So somehow the electrons have lost its elementary particle character when is embedded into a system with many, many other electrons. So the natural question is, where does the electron go? Where does the other piece of the electron go? We can understand it again using this bijective, let's say, this relation between real time and frequency. We know that if the particles are non-interacting, then the Fourier transform of the lesser Green's function is just a delta function. Very good. This is true for the greater and the lesser. Typically, you combine the two and you get the spectral function. It doesn't matter. This is a detail. What you see here is in frequency space, how the spectral function or the lesser Green's function looks like versus the momentum. Okay, just a peak at the quasi-particle energy, just one peak. Now, if you include interaction and you do the calculation, for instance, at the GW level, what you see are several interesting things. First of all, there is still somehow the particle. It becomes a quasi-particle, and the reason why it becomes a quasi-particle is because this sharp delta peak broadened by the inverse of the line. But in addition to that, you see exactly where the rest of the electron goes. It goes into something that are called collective excitations. So you remove a particle, you just don't remove an electron. You also remove a collective excitation in the system, and these collective excitations are called plasmons. Typically, you either add a plasmon or remove a plasmon, depending on whether you add an electron or remove an electron. This is what you get at the GW level. And if you make cuts of this spectral function, it's very nice to see that for momenta below the Fermi energy, you nicely see this broadening of the quasi-particle peak, plus a rather sharp plasmon peak. But exactly at the Fermi energy, the width of this peak becomes exactly 0. And that's a theorem, beautiful theorem due to Lattinger, showing you that if even in an interacting system, in an electron system, at the Fermi energy, the quasi-particles still have an infinitely long lifetime, like in the non-interacting case. This is true only exclusively at the Fermi energy. And of course, you see, it reacquires some kind of width above the Fermi energy. Is this the end of the story? Does the particle just create a plasmon? No, it's not the end of the story. This is true in GW approximation. GW approximation is not the exact approximation. If you go beyond the GW approximation, what you see is that one electron can create also two plasmons, or actually three plasmons, and so on and so forth. So it's a bit like an harmonic oscillator where you are exciting this longitudinal waves inside your system, but is not really like an harmonic oscillator because the distance between this peak is a constant. Okay, so its many-body problem is is always full of surprises. As, when you think you have something, there is always a correction that you have to apply. Okay, so this is my last slide. I hope I managed simply to convince you that the many-body problem is super exciting, because it's not enough to know the interaction between two electrons to predict what happens when you have 10 to the 23 electrons. And this is pretty much with water molecule. You can also guess how two water molecules behave. Okay, you have a nice theory. You know the interaction, effective interaction between two water molecules. You can run your simulations. Things become more, even richer if you have 3 water molecules. And the physics becomes a little bit more richer with 4 water molecules. But if you hope to get waves with this approach, you are doomed to fail. Okay, you need intrinsically a method that deal with macroscopic averages. And at the very end of the game, the Green's function, the density, or whatever else is exactly this type of object, macroscopic averages of intelligent quantities. So to conclude with something said by Anderson, more isn't just more is different. And with this, I would like to thank you all. Sorry, I think I was late. No, okay.
I need, before asking for questions for the plugin, I have to apologize with people attending online. Oh. That no, unfortunately, we had a problem and it's not possible to make questions. So there is no chat. We're trying to solve it, and starting from tomorrow morning, we really hope we can have this possibility. Sorry for that. And now, if there are questions, please.
You were saying that you can use intuition to define the interaction that you should find in the system. So could you please elaborate on that? Like if you, for example, have different types of materials, you should start, but maybe there is something that you don't include, then you don't know.
Okay, yes. Of course, I mean, nothing is so easy, right? It's not that you give me a new material and I'm like a wizard that I understand. I mean, what is, and this is something, when I'm in physical intuition, first of all, the intuition comes with the experience. So try different approximation and see what is the physics and look at what is the physics contained in the approximation. But somehow what is nice of these drawings is that they really contain the type of interaction that you might expect to be relevant. I mean, I guess many of you here are interested in accidents, which are at a bound state of electron and a hole. Now you know from very basic quantum mechanics that if you have a one-dimensional potential, you suppose you have one-dimensional quantum mechanics, right? One-dimensional quantum mechanics, and you start creating a well. And you know that when the well in 1D becomes deep enough, you might develop a bound state. The energy of this bound state is not perturbative in the width, in the depth of the well. And this means that in order to get a bound state, you have to treat the problem non-perturbatively. And this is what happened with an accident. If you want to get an accident, you have to treat the interaction between the particle holes many, many times. So a particle and a hole should scatter, and then after a certain time rescatter, and then rescatter, and rescatter, and rescatter. And this I know from my physical intuition from the basic course on quantum mechanics that is not perturbative. I use this information into the diagram for the Green's function and imagine how the self-energy should look like. So this is the type of physical intuition I was referring to, okay? Or if I want to generate surface dipoles in a material, then I know that I have to start removing an electron from one place and put it in another place to create the dipole. This means many, many particle hole excitations. And that's why people use GW that contains all these bubbles. So with the experience, you actually start gaining an understanding of these different drawings, and you can then nicely combine them if you think that they might be relevant together or combined.
Hello, my name is Stefan, and I'm from the University of Oldenburg. So I have a kind of a, let's say, a meta question. So for somebody who is new to many-body perturbation theory, a lot of this theory is kind of overwhelming at some point, but also it is necessary in order not to do things blindly and to calculate stuff without knowing what's going on. So how do you suggest somebody should, let's say, gain this experience and develop this intuition? I guess there is no certain process, but do you have some suggestions in general and so on?
Well, certainly, let's say, find a
good book.
Find a place to study the rudimentary. I mean, and everyone has his own way of understanding too, no? So, so the best thing is probably to find at least a good place to study the fundamentals, and then get your hands dirty with, for instance, the self energy or whatever you are using, trying to get your hands dirty with that. And also another important thing is to start changing and tweaking and tweaking the knobs and the parameter, changing the parameter to see what are the effects of the various quantity when you run a code to see different results, so that you can start gaining a physical understanding of what happens if you increase this. I don't know, the screening of your substrate, or I don't know, whatever parameters you might change or in your system. So it's yeah.
So I just wanted to add a comment related to the question. I think it also depends a lot on what you are interested in. So in this kind of school, we try to put together what is material science, the ab initio, and what is the many-body problem, so the theory. And then on top of that, we also have the non-equilibrium stuff. So then it depends if you're just interested in computing material properties. Then you can, let's say, use the code, you try to understand a bit, but that maybe just the main concepts. Or maybe you want to take the code and do extra developments. I don't know, you want to describe the exciton and then to describe exciton-phonon interaction. So these are two very different goals, and depending on these, you need to study more the technicalities of the code, the technicality of the theory. It's up to you also.
There are other questions? If not, I would like really to thank Gianluca for his introduction.